2010-2015 with the specializations, and the PhD started from after becoming a university. So once the student joins in KL University, he can do his BTech, he can do his MTech, and he can complete his PhD. Later on, he can be joined as a faculty in the same institute also. So these are the specializations of different research areas for PG, UG, and PhD. And this is the ratio, and this is the research areas. As we are a very large department in the institutions, so many faculty are there, and every faculty will not work in the same domain. Even here also your faculty members are there in the signal processing, in VLSI, and in communications. Like that, we also working in different research areas like microelectronics, MEMS and nanotechnology, antennas design, applied signal processing, biomedical signaling, low power VLSI, atmospheric science and weather forecasting, wireless communication. So almost are touching all areas, all domains of the research in electronics point of view. And these are the three the specializations mainly leading in the department, and one of the domain is the microelectronics, which mostly the VLSI, mostly the devices and circuits, which is heading by myself, and signal processing is heading by P. Kishore, and communication systems are heading by BTP Mother. So we are the leaders for these specializations, and again we have a head of department like your head of department, and after the head of department there is a principal, and after the principal there is a VC. And the department is meant for research in the KL University. EC department is purely research oriented because of so many faculties from IIT, faculties from NITs, faculties from other institutions also we have. So we have a huge research projects in the department from different funding agencies. This is about my department because where I am working, that is my habit to discuss. Right? You are here, wherever you go outside, you will discuss about your family, right? So my institution is like my family, and wherever I am working, I should always represent my institution. And after that, let us discuss about this today talk, which is the nanoscale transistor. And I always believe this statement, which is research. What is research is, maybe you are in a second year level or third year level or fourth year or maybe PG level. Research is not something anything new. The students what we have in our institutions, third year students are doing a lot of research. Many different kind of the projects they are working. Final year students are working on. Research is always to see what everybody has done, what others have done. We should know about what others have done, and we should be in a position to do something new which is not done by others. Right? That is the research. It is not something, a innovation which is not available everywhere. No, it is not like that. Transistor is there from 1947 onwards. Still we are talking about the transistor, and we are saying that we are doing research means transistor is the same, but inside we are doing some modifications. So doing our small changes in the process is also a research. And also research is what I am doing when I don't know what I am doing is also research. So there is my scholar is there here. Once upon a time he is a faculty member here, Mr. Shaukat Baliga. He joined for PhD, and he worked for some time. He did not understand the problem, but now he is in a position to understand his problem, and he understands what research is and what everything. And he is the senior professor in the department, though running, heading by others. We used to take the inputs from people. He is the man from IIT Kharagpur, and he is the knowledge hub. If you use, you will get the knowledge. If you can't use, so wherever we see, it depends upon us how we can utilize the services, how we utilize the resources. If you feel others are waste, we are waste. Simple. If you are learning something from others, definitely you are learning something new. Okay. So last day, two professors came from NIT. Okay. They are from NIT, I am from KL University. If you feel like that, I am waste compared to NITs. I am not a NIT category, I am there in the private institution. But what you need to see is what they have taught, what I am teaching, what you learn from them, what you learn from me is the matter. Institution is only the label. Tomorrow you will be go outside, you are from TEC, and some people will be joining the same industry, they are from IIT. No issue. What knowledge you have is the matter, obviously. Due to so many circumstances, you are joining here. Otherwise, you could be there in NIT or IIT. Maybe some of you. Like that, every person, everything in the universe is valuable and it's a matter. So with that, I always believe that, and I also convey the same to my research scholars and my students. So this is the problem. This is the human tissue, the human body tissue. If you cut, you will see that both the layers. This is the normal layer where you have the atoms or the cells are in a regular pattern, and this is another kind of the tissue. There is a one line is there, which is the barrier. Right? We have a skin, and inside skin there is one more skin is there, and inside that there is one more skin, and after that there are so many nervous system are there. Right? So these are the tissues. If you have a tissue like this, no matter. Both the tissues are good, they are working properly. Your blood circulation, everything will be inside is good. But if you get this kind of the disorder in the tissue, this is the disorder in the tissue which is affected by some kind of the mitigations in the cells. Some, we can say, some kind of the virus, or we can say some kind of the unwanted cells are there in between these two tissues. And this is not in a stable, because when you take the electron is not the stable, it will be move always, right? So here, once this kind of the disorder is happened, the cells are happened between the two layers or two tissues in the human body, this will be spread like anything. That is called the cancer. Cancer will be spread like anything, and it is affected any person. The person is going to face a lot of issues in a short span of time, because inside the cells will be spread like anything. So in the human body, when we have this kind of the problem, we can say that the human body is facing with the cancer. It may be happened in so many parts in the human body. It may be happened in the lungs, it may be happened in other locations in the human body, which is the main concern in the overall world. Getting solutions, some kind of the solutions to detect these kind of the cancer cell is the main concern in the world, because the death rates are increasing. The death rates are increasing like anything. There is no such a pure solutions for such a kind of the disease is happened and it is affected by the human body. That's why cancer will be caused because of certain genetic mutations of the cells like this. These cells are not any foreign organisms. These are not coming from outside. Cancer will not come due to the water. Cancer will not come due to the food. Cancer will not come due to the other things. This is internally mitigations of these cells which is in the disorder. And this rate is increasing, there should be a requirement, and some solution is required to understand about these cancer cells. So in this process, we understand that the cancer is not in one type. The cancer is there, colorectal type, lungs cancer type, breast cancer type, and many of the other type. Among all these, we have chosen this particular domain, that is the breast cancer cell, because it is a very, very important to give some solutions to the breast cancer cells. And we should give some kind of these solutions, diagnosis of particularly those kind of the patients from the electronics point of view. So in this process, we started our journey and we understand initially the normal cell and the cancer cell. Normal cell will have certain shape, normal cell will have proper properties, physical properties, which will not be changed. Whereas the cancer cell doesn't have a particular shape, it will be continuously shift its shape, and wherever it will happen, it will be spread like anything. So this is the basic knowledge we understand, and after that, what type of the cancers, diseases will be happen in the human body. In the entire human body, there are so many parts the cancers may be happen. It is not only in the lungs, it is not only in the breast, it is not only in the even in the brain also the cancer cells are developing nowadays. So from the literature we understand that the breast cancer cell around 11% is diagnosed so far up to the 2018 and 2020. Only 11.6% is diagnosable. That means only 10% is having the solution. 90% we don't have a hopes. And there is a stage 1, stage 2, stage 3 type of the cancers. And also 6.6 the death rates are occurred due to the breast cancers globally in 2018. So there is something is happening in the world, and we need to identify solutions for this. And for that, to understand the breast cancer cells, we have a key factor, that is the one of the experiment, the instrumentation, that is called X-ray mammography. The X-ray mammography is the instrument. If you have a symptoms of the cancer, then you can go and diagnose yourself and will get the reports. From the reports, it will be, I observe that whether you are having any kind of the breast cancer cell or not. Okay, so the drawback of this particular X-ray mammography is, one is sensitivity and specificity. The exact outcome of that particular experimentation is not 100%. That means it is not giving full 100% of the solutions to the disease. And also the specificity. These are the two parameters are saying that the X-ray mammography is not only a one way of solutions to detect the breast cancer cells. So we need to go for the alternative. And the alternative, before going to the alternative, we understand that due to these limitations, the output is reducing to the 67% and 87%. So we are not getting 100% of the results. So in this process, we have seen the experimentation, we have also undergone through the experimentations, and these are well reported in the literature, and even doctors also read those research papers, and later on the reports basis they will suggest the inputs to the patients. So this is the X-ray mammography, which is the very, very high expensive experiment, and which is faced a lot of issues are also, and manpower is required. It is not run by ourselves, it is not done by doctor, it has to run by a special technicians. So this particular entire process is required more complicated. You need to go to hospital. Some people they want to enter into this particular closed container of the X-ray mammography, feel some kind of the suffocation. So they feel some kind of the suffocation, they cannot face this kind of the experimentation, and it is hospital based experiment. You cannot bring it to our home because it's in terms of the closed. And this is the most expensive and difficult job. It requires a lot of skilled persons who can handle this and all. And also the people from the backward areas, from villages, and from the villages also like a backward people, female candidates, they don't have such a knowledge or the awareness to go for this kind of the experimentation and get the solutions for their particular disease. They cannot put some people, they cannot put even efforts also. So understanding of all these difficulties in this process, being as engineer, there should be some kind of the solution is required for these problems. Usually when we face this problem and we go to the hospital, they do the X-ray mammography. After half an hour, they will call you for the report discussion. Okay, they will get these kind of the images. And from these images, the doctor will understand that whether the cell is presented or not. If any signal processing people are here, image processing people are here, can understand the image. In the image again there is a lot of knowledge is required to understand. So what doctor will tell you based on this, he will give you some kind of the suggestions. Sometimes during this experimentation process there will be sometimes there will be false reports also. Others reports will come to some other name and other things. So this entire process will be a cumbersome. So the patients will get a lot of doubts whether that report is correct or not and everything. So all these created some kind of the limitations of the present hospital processing and expecting something from the engineering background, some kind of the portable device for the same cause. Same cause means it may not be give you 100% or some kind of a portable device is expecting in the society from the engineers. Therefore, transistors can do this job. The transistors what we are studying, which is the tunnel based transistors, in short name we used to be called as a TFET. The TFET devices will be able to detect the cancer cells, will provide you some kind of the output. From that output one can understand that what would be the status of the cancer inside the human body. And it is not that complicated and it is a portable device, the cost is less and everything is less, but still it is in the developing state. It is in the developing stage only because of fabricating the device. So far transistors are not really entered into the market and they are limited in only in the research labs. In the research labs they are understanding that this type of the cancer cell can be detected by the transistors. So many transistors are developed but not enter into the market in a commercial point of view. So in that line, what this particular experiment will run is, this experiment will run on the radiation that is connected with the frequency. So that is their method. This method is depending upon the dielectric property. So whenever you pass the radiations, then that will be entered into the human body and there some properties will be changed, optical properties, dielectric properties and all. So here these images are coming and these are connecting with the frequency range. So X-ray mammography can do lot of samples. Every sample is not same. Some sample will have the different kind of the blood thickness. Depending upon the thickness, they go for different kind of radiations. If they go for different kind of the radiations, the frequency will be different. So from this experiment, already it is proved that the breast cancer tissues are exposed to the microwave radiation. If you pass the microwave radiations, these can be detected. This is already proved, experimentally proved. And from that what we have understand that whenever we have a cancer cell, it get more water content. It get more water content, therefore the X-ray once the radiation will be fall on this particular cell, that will be scattered. The scattering will be more when radiation is passed on this particular tissue. Whereas a normal tissue will have a less water content, then the radiation goes, that will not be scattered much. So one very easy understanding from the radiation, microwave radiation goes and fall on this particular sample, and immediately what we can observe in the sense that technicians can observe radiation. And radiation scattering. If more scattered means there is some sort of cells are there. If less scattering is there, that is a normal tissue. Depending upon the processing of this particular scattering of the radiations, they understood that normal tissues will have a less scattering and cancer tissues will have a more scattering. More scattering means the permittivity and other electrical properties will be changed due to because of the radiation passing on through the cells. So your cell, entire cell of its properties will be changed, and among them one of the property is the frequency, and the frequency that is connecting with the dielectric property. Anything you take in this universe, some materials are the dielectric materials. You know, metals are there, semiconducting materials are there, and the dielectric materials are there. Can we use only the dielectric materials for the purpose of PN junction? Can we use? PN junction can be formed from the dielectric materials? No. Okay, we require the semiconducting material to form the PN junction. We require so many semiconducting materials required for the device. Whatever the mobile you have in your hand, inside there is so many ICs are there. Every IC is made by the semiconducting materials only. Other than the semiconducting materials, metals are there, and other material is the dielectric material. So when you pass the radiations to these particular cancer cells, this cancer cell of the dielectric property will be changed due to because of exposure to the radiation. So this is the main idea about the electronic engineer. This is the process. You see the radiation is going, passing through the normal cell, and scattering will be less. And here the same radiation goes and passing through the cancer cell, the radiation will be more and the scattering will be more. Therefore, dielectric property of cancer cell, dielectric property of the normal cell is differ due to because of the radiation. This is the basic knowledge, understand? So dielectric property is our main key parameter. So due to because of the dielectric property, we can able to diagnose these kind of the cancer cells in the human body. So this we have understood from the literature already. X-ray mammography, we understand. X-ray mammography will be undergo with the different kind of the radiations. Therefore, different frequencies are there. One is 50 to 900, and also in terms of the gigahertz also frequency is passing through the cancer cells. That's why you might have some experience. If anybody have the cancer cells, particularly lungs cancer cells, they will go with the radiation effects. Right? They will go with the radiations. Later on, it is having some kind of hope that the cancer cells may be reduced. If you use such a kind of high energy microwave radiation to the human body, the location, the cancer cell will not completely kill, but the cancer cell development will be stopped due to because of high frequency. So whenever you go with different kind of the frequencies, your dielectric constant is also changes. 50 to 900 megahertz and 200 megahertz to 13.6 gigahertz. All these literature says that every cancer cell will be undergo with the different kind of the radiation. We have taken the help of the experimental data, and now we have used these kind of the cancer cells, breast cancer cells like HF578T is the one type, and MDA, MD231 is another type. Like that, MCF7, T470, these are the 4 different type of these cells we have taken to the account from this experimentation. That is already mentioned here, reference number 18. Already experimentally it is proved that at this particular frequency, these particular cancer cells have been diagnosed. And also normal cell. If it is the normal cell, this is the normal. We have taken these 5 kind of the cells, normal cell and the breast cancer cell, and we have used our particular technology, that is the nanoscale technology, with the help of the transistor, and we have diagnosed our cancer cells of these, and whatever our transistor we proposed with some architecture, that is the best way one can able to get the solution. That is the entire the way of our research. And why we are going for the transistor? Because transistor is very small. Nowadays it is available in terms of the nanoscale. Nanoscale means very small. And when we go for miniaturization, then your cost of the device will be reduced, and you can able to move with the device. Earlier laptops are not available, very big size of the computers are available for the same purpose, and we can be able to move. Now we are going with the mobiles, we are going with the tabs, we are going with the laptops. The laptops also, Samsung will have one kind of the weight, and Intel based or like iPhone based, they have one kind of the weight. See, the weight is matter, one of the matter, and inside, why the weight is more and less? Because inside the components are more weight. That's why the entire device is more weight. The weight will becoming less because of the miniaturization. When the weights will be less, therefore more features you can add into the system. So this miniaturization or the scaling will be leading to the output performance. That's why here we are going for the transistors for the purpose of identifying or detecting the cancer cells. Already X-ray is there. X-ray mission itself is almost half of this dias, the equipment itself. So instead of that, we are going with a one transistor, what we are normally seeing in the labs also transistors. Not exactly the same, but it is the same kind of device. So 10 nanometer size, the channel length is 10 nanometer, 7 nanometer, 5 nanometer, people are doing. Such a kind of a very small scale device is able to detecting such a very, very dangerous cells is the innovation. It is the research. Okay. So that is actually our main intention, and in this process we have used the CMOS technology like lithography, oxidation, etching process and all to make our device, but we are not doing experimentally. The device is considered CMOS technology basis. We are assuming some kind of the architecture and we have simulated that, we have designed. Experimentally in the EDC lab, you must have a diode, you must have a transistor, and you are giving input and you are testing the output. But here, we are not doing any experimentation. We have taken the data from the experimentation and we are using the software tool, which is the EDA tool. The title of your the seminar is also the EDA tool, electronic automation. Okay, electronic design for automation, right? So we are using this some kind of the EDA tool here, and we are making this kind of the junctionless transistor, which is based on the semiconducting layer. Therefore, the device will be on condition and off condition. Whenever it is in on, how it is going to be respond? When you give the some sample is the input. We are not giving the only input voltage and output voltage or output current. We are giving some sample into the device, and device is sensing it and providing the output. That's why this is called, this transistor is called a sensor, because it is sensing. And this is the process what we have observed. So we are taking the sample from the human body in terms of the blood and other forms, and that we are considering as the biomarker, and that is the sample. And the sample we are injecting into the device. This is the transistor device. And inside the transistor device, this portion is the cavity. It is the cavity where you can pour your sample. So you pass your sample into this location, and this is the metal, this is also a metal, this is the double gate transistor, this is the source, this is the drain, and this is the oxide layer, and this is the channel. The moment this biomarker sample is entered into this cavity, your transistor should respond it. That means it should be sensing. That means this transistor will be provide the output potential that should be proportionate to the input of your sample. If you give more and more sample, this transistor should be generate more and more potential. So your input sample is proportionate to the potential changes. Therefore, potential changes means that drain current will be changed, electric field will be changed, electric field will change, sensitivity will be changed, threshold voltage will be changed, everything will be changed in the transistor. If it is not responding when you are passing this particular sample into the diode or the device, that means your device is not responding. Your device is not responding means you cannot use the device for the purpose of this class. So here, when we give this sample into this device, in a nanoscale dimensions, this device is called the nanoscale transistor. As this nanoscale transistor is detecting this particular cell, that's why we can use this transistor for this breast cancer purpose, identifying purpose, detecting purpose. That's why this transistor is acting as a transducer. It is converting input sample into the potential, and later on it is providing you the what type of the cell is there, what is the concentration of the cell and everything. So the complete diagrams of the sample will be provided by this particular transistor. And if you look into this device, this is the design of the transistor, and this is the proposed architecture. One can make the design in multiple ways. I can take source and drain, and in between channel. Somebody can take drain and a source. Drain is this side and source is other side. And somebody can take oxide layer in the HFO2, both the sides. Some people they can go for the silver oxide, and you can go with the tin oxide and all. So there is no limit for the design. As a electronic engineer, you can design your device in your wish, but ultimately your device has to be respond to the purpose. So here my proposed device is a junctionless because there is no junctions. It is a junctionless. There is no junction between source and the drain and channel. And the cavity is formed here. You can see this is the cavity where we can inject our sample into this cavity. We have both the sides of cavity. We have gate at the top side, that is the front end, and gate at the back end. That's why it is called the dual gate or double gate transistor. You can make the transistor single gate, you can make the transistor double gate, you can make the transistor multi-gate, which is called the nanowire based transistor. Your gate will be surrounding of your channel, which is the gate alarm. So as you are going for the applying of the gate engineering, that means you are going to improve the output of your device. When more number of the gates will become, then controllability will be more, therefore your device will be perfectly work. That's why I have used here 2 gates. One can also use the single gate. The dimensions are mentioned here. 100 nanometer length is the gate, which is having the cavity 50% and oxide layer is 50%. And both the sides we have done with the same. And we have the oxide layer, which is the thickness is 0.5 nanometer. You can give 1 nanometer, you can do 0.6. So from the literature, it will come to our mind how much we provide. Therefore, we will get the better results. So based on that knowledge, we have given a proper dimensions to the device. We have designed the sensor. This is acting as a sensor. And we have seen the output of the sensor. We have applied several models. We have seen this is the green lines, dotted lines provides the experimental data, which is already done. Experimentally, it is already reported in the literature. Some people they have done. If they use the gate voltages from 0 to 0.7, they have this drain current. And what we have done simulated with the TCAD tool, Atlas TCAD tool, our simulation results are with the blue color. So our simulation results are very much mapped with the experimental data. Therefore, whatever the architecture we have proposed, this architecture is having some meaning. If it is not mapped with the experimental data, then there is a more difference is there with the experimental data and our simulation data. Our proposed device is not perfect. So our proposed device, after so many number of simulations, our final architecture simulated data, the drain current data, which is one of the characteristics of the transistor, mapping with the experimental data. So we have confirmed that our proposed whatever the transistor we have taken, this is the perfect architecture for the detection of the cancer cell, because it is mapping with the experimental data. And the dimensions what we have taken, all these are by changed number of times by lot of simulations, and after that we have confirmed. And the proposed device is able to detect these kind of the cancer cell. If you have a cancer cell, the dielectric property of this particular cancer cell is K equal to 22. This cancer cell is K, dielectric constant K is 24.5. And this cancer cell is 32 and another one is 27.5. That means cancer cells are so many in the human body. So every cancer cell has its own dielectric property. If you know the dielectric property, you will get some kind of the transistor. That transistor is able to detect it. If the dielectric constant is changed, again you need to change the architecture of the transistor. So in this process, we have taken this 4 and our proposed device is able to detect all these kind of the 4 type of the cancer cells and also the normal cell. Normal cell of the dielectric constant is 4.5. For your information, during the COVID situations, there is no solutions initially from the electronics point of view, but later they got some kind of the solutions from the electronics to detect the cancer cells. And one of the solutions from the transistor point of view is the cancer cell of its dielectric constant is understood 4.1. 4.1 is the dielectric constant of the coronavirus. And based on the dielectric constant, the researchers have made a architecture of the transistor, and later on they have fabricated and published in the market also. And it is available now in the abroad. So coronavirus dielectric constant is very, very less. It doesn't require any radiations to stop. That's why there is no any kind of the radiation kind of the techniques used for the coronavirus. Right? So where we see the breast cancer cells will have a very high dielectric constant, so which will be connecting with the radiations. So in this process we have designed our architecture, and we have seen that the cavity thickness, if you change, then you can able to detect the more and more number of the cancer cells. What we have seen earlier, the cavity thickness is 5, 4 and 3. We observed that the potential is changes, and the potential is good for the cavity thickness is 5. Therefore 5 will be a good solution. You can take the 5 thickness of the cavity. So we have finally optimized, but before optimization we have to come to conclusion based on the results. And here you can see how the electric potential is formed inside the channel. So if the channel length is, the cavity length is 5, 4.4 and 3, the potential you see compared to here, the potential is less here, and compared to here the potential is less here. So the potential is very, very good when the cavity thickness is 5. So we have fixed the cavity thickness appropriately. And also with the same dimensions of the cavity thickness, we have also seen the energy bands. We have valency band and conduction band, right? So that valency band and conduction band of the relation we have seen for the 5 nanometer cavity thickness 4 and 3. And 3 is providing the best tunneling. The tunneling capability is good for the thickness of the cavity is 3. Also we have seen the drain current, which is the most important one. Output of the transistor is the drain current. So the drain current we have seen for the 5 nanometer thickness 4 and the 3, which all these electric field, energy band and drain current will be provide you fixing of the cavity thickness. The cavity thickness among the 3, 4, 5, we have fixed the thickness, which is ultimately providing the better results of all these 3 parameters. So we can conclude that, so the parameter 3 nanometer, 4 nanometer, 5 nanometer of the cavity thickness, the current, ion by IF ratio, transconductance, subthreshold swing. Among these performance parameters of the transistor, for 5 nanometer, ion current is good, that is 0.431317 milliamps per micrometer. So when we are expecting more drain current, which is the good of this. So this is the good, that's why we have fixed the 5 nanometer cavity thickness. And also we have changed the variations of the L1, which is the thickness of the oxide layer. The thickness of the oxide layer is considered here, that is the silicon oxide, and we have changed the silicon oxide thickness. When it is increasing, surface potential is increasing. You see 20 nanometer, 30 nanometer, 40 nanometer, 50 nanometer. If you are going with the 20 nanometer to 50 nanometer, where we have a 50 nanometer which is having a higher potential, that you can observe here from the green. So one is cavity thickness, the other one is the oxide thickness. So oxide thickness should be approximately 50. And for the same, the energy bands also seen. The energy bands for the 50 is good, and also we have seen the drain current similarly. So the drain current is also providing better for the 50 nanometers. So 50 nanometer of the oxide thickness, 5 nanometer of the cavity thickness is fixed, and we have designed the device. So when we compare with the thickness of the oxide layer 20, 30, 40 and 50, ion current you see 0.4313, and for 50 nanometer it is 0.4323. Maybe it is in terms of the floating point it is very small, but in terms of the current which will play a vital role. So we have fixed the 50 nanometer thickness of your device. And then we have also seen the dielectric constant, what type of the dielectric constant will detect this particular device. In this process we have taken these 5 types, and all these 5 types we have seen when we have the cancer cells and the health cell, we have seen potential energy and the drain current. And we have noticed that the health cell is having a less current. Whenever cancer cells comes, for that your transistor is detecting the drain current is more, because the electric constant of the cancer cell is more than the health cell. Your health cell is having the dielectric constant 4.5, and your cancer cells is having 22.5, 24, 27 and 32. So when dielectric constant is increases, your drain current is increases. So that provide you a path for identifying the cancer cells in the sample. The drain current, that is the sensitivity of the drain current also seen. Sensitivity is also good when the cancer cells are presented. Our device is providing the high sensitivity. And we compared when we have a healthy cell, when we have a cancer cells, the device parameters are changed. And particularly when without the cancer cell, with cancer cell, there is a difference. There is a difference in the threshold voltage. There is a difference in the transconductance. There is a difference in every way. So that means your proposed device, your simulated device is perfectly doing the simulation of your samples. And also we have changed the dielectric constant for the threshold voltage, for the ion and transconductance and other purposes. In every way it is showing that when cancer cells are presented, your device is providing the better sensitivity. So your transistor is responding and providing high sensitivity means your cell is having, your sample is having the cancer cell. In this process, you can take more and more samples and you can able to test it with the help of this particular transistor. And as this particular work is limited with the simulation, and we see here the threshold voltage, this is the delta VH is the sensitivity of the threshold voltage, delta IR is the sensitivity of the current, delta GM is the sensitivity of the transconductance, delta SS is the sensitivity of the subthreshold stream. So everywhere this is the cell, healthy cell, these are the cancer cells. This is the healthy cell, these are the cancer cells. In every case, every sensitivity of the parameters providing that healthy cell is having the less sensitivity, your cancer cells are having the higher sensitivity. And particularly this particular T470 is having a higher sensitivity, which is very very high compared to the healthy cell. This particular information will provide you, this belongs to one kind of the cancer cell. We are not dealing anything with the experimentally, but with our proposed device, we are able to detecting these particular samples. It means whatever the device we have proposed, the device can be fabricated. Once it is fabricated, whatever the results we are getting theoretically, you will get experimentally the same data. So that means the proposed device is able to detect even experimentally also these 4 cells. Whatever the 4 cells we have mentioned, and the proposed device, whatever we have proposed, the architecture, we have compared with the other members. Before us, there are many people, they have done it. They have also proposed the architecture, but their architecture is something different. So your TEC building is like a C shape. Okay, some other engineering college building will be in L shape and also in U shape and some C shape like that. Architecture is something different, right? Our device is like whatever I have shown, and others device architecture is not like us. Because of our architecture, we are able to improve the sensitivity compared to these people. That means whatever our device we proposed, which is the best among these many people, which is already reported. So compared to the other people in the society, what we have done is always better. It should be better. Then we can proudly announce that this particular proposed device architecture can be recommended for the fab, and that fabricated device can be able to detect the breast cancer cell. And we have compared our particular device with the one of the already recently published work, which is reference number 36, and we have compared with every cell from healthy cell to the cancer cells. In every way, our data, the proposed data, is far better than the previously existing data. So, based on this, the conclusion of this particular research work is there is a requirement for the detection of the cancer cells for these 5 samples, and in this process, and being as an electronic engineer, a transistor can be able to design. Therefore, that particular transistor can be able to identify the cancer cells, and later on you can compare your work with the experimental data. If your work is mapping with the experimental data, the same you can fabricate it, and you can go for the patent, and you can go and you can release that particular device into the market for the commercial purpose. That is the overall the summary about my work. And this is, we are in the phase of designing, and we are also comparing the others, and now we are going for the fabrication. So for fabricating this, we require the clean room, which is a very, very highly sophisticated laboratory, which is available in very rare places. So with the help of the collaborator, in future maybe we will fabricate, and therefore real samples are also not available. So who will, if I ask you sample, will you give? You cannot give. So we have to approach the hospitals and we'll get the particular samples where the cancer cells are, patients' cancer samples, and later on these hospitals and fabricated device should be collaborate, then a real-time experimentation can be done. So which is the huge job of the researcher, because it is not possible in academic institutions. That's why we are having a collaboration with the hospital doctors, and already shown this discussion into the aims in the Mangalagiri. And once we fabricate that device also, we will bring and we will go to the hospitals and we will test it. Once that is done, then later on, based on the terms and conditions of the hospitals and the institutions, it will be further processed. So these are the some references to work that, and I will give you in 5 minutes. I will give the glimpses about the research activities what we are doing in our K University in my laboratory. So I believe that the success of teacher in academics is depending upon research and publications. Many of your teachers can understand this. We are a teacher, we will come to the class, we will teach. That's not, now it's not a it's only some part of the job. We have also do the research. We have also to publish. So now teacher job is becoming so complex. It's not a purely teaching. Okay. So academic success of teacher is always depending upon his research and its publications. And also we may not be get the publications immediately. Today if you start your work and tomorrow you may not be getting it. I started this journey in 2004 and today I achieved something. So almost 15 years of my journey, I have come to certain stage where I can able to show some data. So like that, this research activities not come into the my account or to my lab or to my institutions in overnight. It will have a lot of background, lot of efforts are there. This is the one of the very important which we all are facing in the research. To steal ideas from one person is the plagiarism. To steal from many people is the research. If you copy others from one person is crime. If you copy from others, it is okay. If you copy your work from others, it is the duplication. If you see others' work and do something new to that, add to that, then that is the research. So research what you are supposed to do in your major project in the final year or in the term paper or in the minor project, it is not something which is not available in the world. It is available. You are going to add some element into that particular already existing problem. So that way you need to understand about the research, and we all are started our career with that motto only. I already mentioned last time, Professor Buka was also mentioned, all our aim is only to promote research activities in terms of micro and nanoscale level, nanoscale devices level. So you have mental graphics, which is the circuit level, right? Mental graphic is there. So which is the circuit level. This transistor can also be designed in a circuit level. You can use for the inverter, you can use for the SRAM cell, you can use for some other purpose. But what is the matter here? In your transistor here you are using the nanometers. Whereas in mental graphics you are limited with the 130 nanometers. So before 130 means less than 130 nanometer, you are not able to design anything in the mental graphics. So circuit level simulation is something is possible at any technology node, but device level simulation is a particular along with the technology. In the mental graphics, if you use 180 nanometer also is possible inverter. But really your NMOS and PMOS for the 10 nanometer, which is not possible in the mental graphics. So devices are very important. Devices knowledge is important to understand. So we always motivate about our work in terms of the micro and nanoscale devices like MEMS, nanotechnology, nanoelectronics. Today the world is about the nanoelectronics. Whatever you take from the electronics point of view, traditional devices doesn't have weight. Everything is now smart. Everything smart means sizeless, weightless, costless, and better performance. Best features is required. So these are coming from the micro and nanoscale devices because of the process, because of its technology. We are able to reduce the size, we are able to reduce the cost, we are able to improve the performance. Like switches in so many aspects like satellite applications and other applications, RF MEMS filters and RF MEMS devices for the reconfigurable antennas, and also physioelectric energy harvesters, MEMS drug delivery systems, MEMS kidney on chip. As MEMS kidney on chip means human body is also facing with the single kidney people is facing the problem. And what is the solutions? So some solutions are there. So based on that we started some work on the MEMS technology on the kidney on chip. We artificially take the kidney, we observe the practical kidney, what it is functioning, how much sodium it is taking, how much potassium it is taking, and how it is mechanism is processing, and why single kidney cannot be run for a long time. So that kind of the work. So we are taking some artificial chip as a kidney and we are working on that. And also drug delivery systems. If you are facing with some problem and you are, suppose headache, you are taking a medicine. Your head is here and your medicine is going to your stomach, and later on it will go to all parts of your body, right? But why unnecessarily your drug is delivered to the so many organs? You are having some disease in some location, you should give some, your drug is also into that particular location so that that location will get cured. But you are taking the tablet. So the tablet will be dissolved into your stomach, and later on it will be move on to every part of your body. Some chemical will also go to the heart, some chemical will go to the kidney. That's why whenever you are having some kind of the headache and other kind of the diseases, you cannot take some different kind of the tablets, because those tablets will be damage your kidney and other parts. So our intention is we should deliver the drug into a exact location of the body. Suppose I want to give some drug into this location, and I developed the chip. The chip I will place here on the human body. Therefore, later on, and this drug will be injected into the exact reserved location. Therefore, organs doesn't require and doesn't affected by the unwanted substances of the chemicals. And these are the areas we have done, and we have the couple of faculty who are working in this. And also, I am running these in the KL University from past almost 70-80 years, and these are the people, they have done their PhD from different parts of the country, and we have some funded projects, and we have some tools so that they are available in our research lab, and with the help of the tools only we are doing computational work. We are not doing experimental, because experimentation is connected with so many aspects. It requires sample, it requires permissions from the government, and also we have to approach the doctors and all. That's why whatever we plan, that we will be execute with the help of the tools, console software tool and Intel Suite HFSS and also TCAD tool. With the help of these we are doing, and these are the people behind me working with me, and because of them I am able to do so many of research problems we have solved. And all these peoples, almost everybody has got their doctoral degree, and there is a person who is now in CBIT, this person who is here and he completed PhD, and she has completed from Vienna Vignan Jyoti, she is completed, and he is completed from Central University. So these are different people. This person is worked on antennas, he is on MEMS, he is on RF MEMS, he is on bio MEMS, and he is on FinFETs and RF MEMS. So for their PhD program they have done, and one person cannot do research, always we have collaborations. That is the reason your principal called us, because you want to collaborate with KLU and also with NIT. Then only your institutions will get some fruits. Okay, like that I also collaborated with some people, and from all these guys I have arranged talks like this in my institution. Some talks are online, some talks are offline, and we have acquired some knowledge from them, and we understood some of the facilities, what is required, we have utilized in their institutions. And these are the models which we already done, and these are the projects we already completed, and these is all are published in high-end journals like IEEE, Springer, elsewhere, Taylor and Francis, in all these works, whatever the work done in my lab, my target is always to be published in a high-end journals. So all these different models based on the MEMS, based on the nanoelectronics, based on the nanotransistors, and this is one of the area where we are working is the automobile robot. So the robot is able to move forward and track something, and also lift something, and also bring something to our exact locations. So most of the robots are nowadays in the indoor applications are using for the service purpose, right? So this is the one of that model. We have developed the architecture, the FPGA based architecture for doing of this implementation, and that is the PhD work of this guy. She is from the DVRIT, and all these models finally ultimately it is available in the now in the IEEE Explore. That means all are published, and we also organize the events like this. So otherwise we cannot do all these many credentials in our department, and every year we used to organize, we used to bring the people from IIT, NIT and from abroad, and we will show our models, and if we want something we will try to get it their help also. That is the reason we have done all these many of the things. So far the number of the international publications what I have in my lab on my name is 185. In fact it is 189, I think 189. So 189 publication is an imaginary task as a single person, but because of the collaboration, because of some planning, something 189 publication is there on my name. You can search in the Google Case University, you will get it. All my 189 publication in the Scopus database, all are published in these journals. And I have also completed some funded projects, and also some attended some workshops, some guest lectures, some kind of the conferences, and 7 PhD students completed means everybody has to work for 3 years. Once 3 years if you work, you have done some work, and your work will be published and patented, and then you will be awarded with the PhD, then you can go into the market. So 7 people they have done with me, and few more are working. And many opportunities are there for this nanoelectronics in the industry. In real estate industry is the now a booming industry. So that's what I mentioned yesterday also. 4 companies are coming to the industry, means the academic institutions. So we are the big institution, we are bringing, okay, fine, no problem. For you there is online interviews are there. For the mentor graphics, you have already software tool. Why can't you ask the mentor graphics people to recruit your students? I have given this instruction to the HOD also. I think probably future you may be called the mental graphics guy to recruit your students. One student or two students also fine. The package for the mental graphics is 18 lakhs. The core company 18 lakhs means you can understand your life even after some years. Like Bosch is also there. Bosch is recruited around 300 students from KLE. And some of the students they got it Bosch through online. Through online there will be so many industries now open their calls. So all of you are having basic electronics. Wherever you go to attend these, all the companies they are asking simple basic electronics. Simple basic EDC, simple basics of your electronics. So this is all about my one, and if you have any doubts you can ask. Otherwise I would like to thank to the conveners who have called me for this event, and thanks to your head of department, your principal, and thanks to my head of department Dr. M. Suman, and also to my management Sri Kode Sachinarayan Garu, for providing this opportunity to discuss about my some research part of the work with you. Any doubts you have? Now the forum is open to discuss. Yesterday also one professor has mentioned NIT, Dr. Kavicharan. Dr. Kavicharan has completed his B.Tech from a college level. College level from Mahbub Nagar, like you. Okay? Don't feel that negatively, always think positively. Now he is in NIT. Okay? He is a very, very poor background area. Mahbub Nagar means they doesn't have even water also. It's a dry area. We are far, far better than Mahbub Nagar. Anybody is there here? I think nobody is from Mahbub Nagar. Very dry area. From the dry area, one person completed his PhD and now he is working as a government employee in NIT means it's because of only planning. You see how he was down to earth. Being as a government faculty, he came to TEC. Only to share the knowledge. He did not expect anything from you. So always participate in the question and answers. Yesterday he was discussing with me while we are going. Students are not in a position to ask any questions. If the same Kavicharan will come to KLU, some questions will be posed. Why not you? You understand? Your background may be anything, your family may be anything, there is no bars to settle your life. So learn always new things, learn the new paths, get the knowledge from so many people. Thank you.
We all got a better awareness regarding fatal issue of breast cancer and also how our electronic devices like transistors can detect such issues. It's great, it's helped a great for our students as well as faculty to choose their research domains, and your talk is very much motivational in a specific domain, and you are all inspired in your research areas and researches of your students. Thank you, sir, once again for your spending your valuable time, and we all congratulate, sir, for your publications and your future work. And thank you for your spending time.